Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Hi, Dr. Martinez. Thanks for meeting with me during office hours. I need to refine my presentation on exoplanet detection methods, and I have a lot of questions about transit photometry and radial velocity techniques.
Hi, Mark. No problem. Those two methods are central to modern exoplanet science. Why don't you tell me what you already know and where you want more detail?
I understand the basic idea of a transit. A planet passes in front of its star and the brightness drops, but I am not clear on what exactly the light curve tells us and what its limitations are.
Good starting point. The depth of the transit is about the ratio of the planet area to the stellar disk area. That means the transit depth gives you the planet radius relative to the star. The duration and shape tell you about the orbital period and impact parameter.
So depth gives radius. How precise is that measurement in practice?
Precision depends on the photometric stability. Space telescopes like Kepler and TESS avoid atmospheric noise and reach parts per million precision, which lets us detect Earth-sized transits around Sun-like stars in favorable cases. Ground-based surveys are useful for larger planets and bright stars, but have more noise from the atmosphere and scintillation.
That explains why missions like Kepler found so many small planets. But transits only work if the orbit is edge-on right.
Exactly. Transit detection is strongly biased toward systems with orbital planes aligned nearly edge onto our line of sight. That means many planets never transit from our perspective. The geometric probability of transit decreases with orbital distance.
What about false positives for transit? I read that eclipsing binaries can mimic planetary transits.
Correct. Background eclipsing binaries, grazing stellar eclipses, and blended light can produce transit-like dips. To confirm a candidate, we often use follow-up radial velocity measurements, high-resolution imaging, and centroid motion analysis to rule out blends.
Okay, that leads me to radial velocity. How exactly does that method measure planets, and what does it give us that transits do not?
Radial velocity measures the Doppler shift of stellar spectral lines as the star moves in response to an orbiting planet. The amplitude of the velocity wobble depends on the planet mass, the orbital period, and the inclination. From the velocity curve, you get an orbital period and a quantity called m sin I, which is the minimum mass.
M sin I, because of the inclination degeneracy. So if the system does not transit, we can't get the true mass.
Right. If there is no transit, the inclination is unknown, so the true mass could be larger. But if we do have a transit, we know the inclination is close to 90 degrees, and combining transit radius and radial velocity mass gives you the planet density.
Density is crucial to determine composition. Can you give an example where combining both methods changed our interpretation of a planet?
A classic example is the Kepler planets, where many small radius planets were followed up with precise radial velocity or transit timing variations. For some of those, the mass measurement showed they were much less dense than rock and likely mini-Neptunes. In contrast, other planets of similar radius had high densities consistent with rocky composition.
You mentioned transit timing variations. How do those fit into the detection toolkit?
Transit timing variations, or TTVs, occur when gravitational interactions between planets cause departures from strict periodicity. Measuring small deviations in transit times can reveal additional planets, including ones that don't transit. This method was used to confirm multiple planet systems from Kepler data.
So TTVs can detect non-transiting companions. That is interesting. What about limitations of radial velocity measurements?
Precision is a big issue. Instruments like HARPS reach meter-per-second precision or better. Stellar activity or spots introduce noise called jitter, which can mask or mimic planetary signals. Long-period planets require long observational baselines and careful modeling of stellar signals.
I have seen mention of the Roster-McLaughlin effect during transits. Where does that fit in?
During a transit, the planet hides part of the rotating stellar surface, and that creates an anomalous radial velocity signal. Measuring that anomaly gives the projected angle between the stellar spin axis and the planetary orbit. It is a specialized use of spectroscopy during a known transit.
How do surveys choose which method to use first when searching for planets?
Large photometric surveys are efficient at finding many candidates quickly, especially short-period planets. Then the brightest candidates get radial velocity follow-up for confirmation and mass measurement. For bright nearby stars, radial velocity surveys also search directly and can discover planets that we later try to see in transit.
What about biases in the detected planet population from each method?
Transit surveys are biased toward short-period planets and planets around small stars because the transit probability and depth are larger. Radial velocity is biased toward massive planets close to the star because they induce larger velocity amplitudes. Both methods complement each other, and combining them reduces selection biases.
Could you summarize the main reason researchers combine both methods for characterization?
By combining the transit radius with a radial velocity minimum mass, you can estimate the planet density and distinguish between rocky and gaseous worlds. That combined information is essential for understanding exoplanet structure and formation.
That sentence will be perfect in my presentation. Any final tips on explaining technical terms to my classmates?
Use simple analogies for the physics, show actual light curves and velocity curves as examples, and highlight real cases like the first radial velocity detection of a hot Jupiter around a sun-like star and the Kepler statistical discoveries. Emphasize strengths and limits of each method and how follow-up observations confirm candidates.
Great! I will include examples of Kepler discoveries and HARPS follow-ups and a slide on TTVs and false positives. Thanks a lot for your time.
You are welcome. Email me your draft and we can tighten the technical explanations. Good luck.
Listen again to part of the conversation, then answer the question.
By combining the transit radius with the radial velocity minimum mass, you can estimate the planet density and distinguish between rocky and gaseous worlds.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.